Hi. Hi, everyone. I think we're here to develop RF products. It's good to play with gateways and so on, but the aim is to have really RF products up and running. And to do that, I think there are two ways. The first way, the easy way, is to use an RF module, but there might be also a need to implement the RF device on your own PCB. So here, the aim of the presentation is to show you how to go from the reference design to an optimized RF solution. So a few words about me so that you trust me when I'm saying something. I'm Olivier Prevost. I'm an RF application engineer working from Semtech. I'm based in Switzerland, in the French-speaking part of Switzerland. And actually, I've been working in the semiconductor industry for 20 years, and in RF in particular for 20 years. I started my career in Philips, NXP, and then I went to the Swatch Group and finally Semtech. And as application engineer, I've quite often heard that, sometimes you don't even know if your device is acting correctly, behaving correctly from the RF point of view, if you have the right performance and so on. And it's a little bit of magic. You need to rely on those strange RF guys, those strange gurus that can see that 1 picofarad capacitor is meeting here at this point. But it's not completely magic. It's not completely black magic. There is a whole theory behind that. There are ideas, concepts. There are tools that are being developed to make your developer's life easier. And one of these tools is the reference design. So starting from simulations, PCB simulations, I moved to tests, optimization. I'll describe a little bit the process afterwards. Then characterization over temperature, supply, and so on, to finally check that you are able, that this reference design is able to pass all the RF certifications. And what does it give you at the end? It gives you a schematic, a PCB, selected bill of materials, so the right components to implement, so that you can have the right device performance as written in the datasheet. It's not always the case. And if you copy this layout and you take those components, you will have the right performance and you will be most likely able to pass the certifications in your application. So here I describe briefly an example illustrating our brand new device, the SX1261. So it's, as Nicolas said yesterday, we announced the SX1261. Actually, it's a whole family, 3 devices, so much smaller, half the size of the previous generation. Reduced current consumption, we divided by 2 the current consumption in RX mode. And so we have the 1261 for high efficiency, up to 15 dBm. 1262 for high output power, 22 dBm, so 140 milliwatts if you need high power. And for the Chinese bands, dedicated device 1268. Now we have to breathe. A big dive into the reference design itself. So we have here the crystal or the TCXO to provide a reference clock, 32 megahertz reference clock for the RF. Then we have a DC-DC converter to really optimize the power consumption. So we need a coil for that. And we have a set of regulators and decoupling capacitors to filter out really the RF noise and the supply noise. And on the right side, it's really the RF part. We have separated, I've designed separated RX and TX path so that you can optimize really the power transfer and the reception path, and those two are linked, are connected with the RF switch. Sometimes I have customers that just don't want to use the reference design I've made for them. I don't think they are the kind of people that want to live dangerously. They have very good reasons for that. And the reason is that they have different constraints in the application. This is an example of a module made by our friends from IMST. And you see here that here's the RF path. You cannot, or we couldn't just copy-paste the reference design. We don't have the straight RF lines, so we have to tune. Or we had to bend the lines, and finally, in RF, modifying the reference design implies tuning. So I will focus first on the TX part, because I think it's most important. You want to be sure that your message will be received by the gateway. And actually, there are two main parts. So in blue, we have the RF coil to supply the integrated PA. And in green is the most important part, the TX matching stage. For the PA, the integrated PA, so it's high power PA inside the 1261. For the PA to deliver the right output power, you need to provide the right load to the PA so that it can generate the right output power and finally the right signal for your application. But also, you want to minimize the power consumption. You don't want to burn your battery after 1 day of usage. So you have to present really the right impedance to the PA. But every PA also generates RF noise. And this RF noise can be a problem in your application. You have to ensure that your RF noise does not exceed a certain level. And that's the aim of the second stage here, the purple stage. So harmonic filter, so that you reduce the RF noise to its minimum. A few words on this, this optimum impedance. It's actually the impedance that you present to the PA with, okay, let's see if it works, yes. With those LC caps here, if you present a 50 ohm load here at this point, you have this LC cap that transforms the 50 ohm to the opt point, so the maximum efficiency point, I would say. How do you obtain that? If you don't follow the reference designs, you can use, I have used a simulation software, basic simulation software, Smith chart tool, so that you calculate the LC values. Finally, you have to implement them in your application, and you measure your output power and the consumption. So the aim is to maximize the output power and minimize the consumption. And if you're lucky, it works the first time. Most of the time, or maybe I have not been lucky, so I had to tune, and test, and so on. So it's a really an iterative process. On the harmonic filter stage, so it's really important. So back to here, the TX matching is important to provide the right amount of power with the right consumption. But if you have a very good power but very bad harmonics, you won't be able to use your device. So the harmonic filter is really, really important too. And I've implemented the harmonic filter in 2 steps. First, second harmonic filter, so it's actually a LC cell, parallel LC cell that acts as a notch filter. So you see here on the right, top right, this is the attenuation versus the frequency. So you see that everything passes unless a precise frequency. So first to filter out the second harmonic, and then a classical pi filter, here a low pass filter in pi, which has this kind of attenuation actually to filter out the higher component values, higher frequencies. Finally, if you put everything together, we have this kind of behavior here. You recognize the low pass filter and the notch here. Once more, if you are lucky, you just reuse your simulation software, put the components, and it works. Otherwise, you have to fine-tune. But why do we have to fine-tune? I mean, we have simulation software for that. It's not as I was in the school, we had to draw on the Smith chart and so on. Now we have very good tools, but why do we have to tune afterwards? Because every software has limitations. Very basic software have very, let's say, large limitations. There are very powerful software that are very precise. If you have a good model of your PCB, of components, you can be very close to your target, but this requires a lot of time to play with the tool, have the right simulation bench in place. So finally, what I've chosen is very basic Smith chart tool that I used not to give me the right component values, but just as indication. So which components has which impact on my impedance. So where to play, actually. And finally, so not sure you can escape that. It's a tuning process. So you implement components, you measure, modify, measure, and here, so be careful. It's not mandatory to use a blade. Don't cut your veins in case it doesn't work. It's it's to cut PCB traces can be useful to implement some probe points. On the RX path, it's more or less the same idea. You have to optimize the power transfer from the antenna to the receive path. You don't want to lose 10 dB because you're not matched. So same approach. You can use simulation software to move, let's say, or match the LNA impedance to the 50 ohm of the antenna. And afterwards, you need to test. So you put values that you get from simulations, you measure. So here for the RX, it's good to measure with a network analyzer that you are at the 50 ohm point. So it's what I've done here. Ideally speaking, you should be here right in the middle, in the frequency of interest. And you can check also that you've minimized the loss. Here it's the loss or the mismatch loss versus frequency. So if you have the minimum loss, then it means that you're matched. So once more, measurement, tuning, measurement, retuning, and so on. At the end of the process, you need to check that your device will be able to pass the certification. So until now, we've measured with RF cables, but Fabien told us that sometimes when you put the antenna, it doesn't behave the way you expect. So you have the PCB, which has some effects. The battery, the housing affects also the behavior of the device. So you need to check that everything goes right before going to the certification house because it's awfully expensive. So here I've used this kind of small chamber here, but you can do also outside in free space. It's more or less the same behavior. But one thing important is that you have to take some margin for the harmonics, especially, because most of the time, when you use the antenna and you implement the battery and the housing, you will have degraded performance. One thing I haven't mentioned, or I kept on purpose the mystery on one thing, is this famous opt impedance, the optimum impedance that you have to present to the PA to have the right output power and the right consumption. How do I determine this opt here? It's done with a, let's say, kind of mystic term called load pool. So it's a very, very basic test and easy to do, actually. So the aim is to present a variable load here. So with the impedance tuner, you present a load on the PA. So here I've modelized only the pins here. You modify the load until you get the right power, but be careful once more with the lowest consumption. And when you've got the right place for your impedance tuner, then you just switch or you put a VNA network analyzer instead of your device and you measure which impedance you have to get, you have to present to the PA to get this performance. So this is this famous opt here. And how does it look like? I mean, the result that you get. So each point here is a precise impedance that I've measured. And you see that there are two special points. The red point here is the maximum output power. So you can get, let's say, 14.5, even 15 dBm, but you will burn a lot of current. So what you want to have is actually the highest efficiency. So maybe slightly less output power, but a very good consumption. But one thing here is that your Z-opt depends on your application. So it depends actually on the frequency you operate or you work at. So you won't have the same Z-opt at 150 megahertz and 900 megahertz. It depends on the output power. So depending on the loss you will have on your antenna, sometimes you have to increase a little bit the power. So the components here values, or the Z-opt, and then the component values will be dependent somehow on the output power you want to use. And of course, therefore, it depends on the device. You don't have the same Z-opt for 1261 and 1262. We can provide, you don't have to run through this load pull process. It's not mandatory. We can provide the Z-opt if needed. The toolbox, my toolbox and the RF guide toolbox. So soldering irons. Did I say that you have to tune? Yeah, so now I say that you might have to tune. So you need soldering irons with fine tips, components, RF components. Smith chart tool, for me it's very basic. It's difficult to avoid to use a Smith chart tool if you want to tune. Spectrum analyzer to measure the output power that you have and the harmonics, very useful. And if you want to play with impedance, then you might need a tuner, impedance tuner, you might need a network analyzer, and some patience and time. To conclude, I would give you a personal anecdote here. So I'm a runner, so I used to run sometimes for long runs. And for my Sunday morning run, I have most of the time two choices. Either I go for a short run close to my house. It takes 1 hour, and my wife is happy because I'm back soon. Otherwise, I go for 2, 3, 4 hours in the mountains. And it's nice because you see nice landscapes here. It's the Alps here, and a sea of clouds above Switzerland and the Swiss lakes. So it's really nice, but actually it takes a lot of time. It's quite risky because you can, let's say, fall and break your leg. If you're in the middle of nowhere, then you're screwed. And also, you might finish sometimes not so fresh. What I have to say. But I would make a parallel here with the application development and product development. There are two ways. The easy way is to reuse the reference design, fast and efficient, or you can go the long way, and then the more freedom, the more distance you take from the reference design, then the longer and the more difficult your job will be. At the end of the process, what you want to achieve for the 1261 is 14 dBm output power after the antenna, and with less than 30 milliamps current consumption, and a sensitivity down to minus 137 at SF12. That's it. Thank you. Yes?
I think yeah. Do you want the mic? Do you want the mic maybe?
My name is Andries Lohmeijer, also ham radio and RF designer.
Yeah.
Does Semtech provide scattering parameters as parameters of the device to run the simulations?
So we do provide the Z-opt or the impedance for the
yes, but also for the complete frequency range, not only the ISM band frequencies.
We do provide for your frequency of interest, actually.
Okay.
Yeah.
And the other question is, in the RX path, you standard don't have extra filtering, but it might be interesting to reduce adjacent channel interference.
Yes.
But it will pay, it has a penalty in the form of less sensitivity. Is it wise to implement RX filtering?
So I've implemented a basic filter in the RX path as well, to reduce a little bit the noise, I would say. So it's implemented in the reference design. I didn't go into this direction because it goes into a specific and complicated concepts, but it's done already. So the sensitivity that I obtained is with this filter. Thank you.
Wait, hang on.
Hello, my name is Timur. A long time ago, we see the same situation with the Bluetooth, that we need to have a huge part of RF designs to matching TX pair or X pair. But now we see that we need the same, the balloon and one or two matching components. Is it possible to make the same with with LoRa technologies, moving parts of components inside the chip? And for customers, is it need to the diagram Smiths and RF parts matching? And that's all. And the second question's about the antenna diversity technology. It's able to evaluate it inside the LoRa technology. Thank you.
So the first question, so if it's possible to integrate part of the matching inside the chip, it's possible, but the issue is the frequency. So for Bluetooth, you operate at 2.4, so your RF devices, I would say, are small. Your RF coils are small, your capacitors are small as well. Here for 800 or 900 megahertz, it's definitely bigger, so it doesn't fit inside the chip unless you want to have a chip this size. So it's better to do that externally, and of course you have to play a little bit with the hardware to tune it. Then your second question was regarding antenna diversity.
Yes.
So it's definitely possible to implement that. It's good to be sure that you don't have gain into a certain direction and let's say a zero into another direction. So it's possible to do that. There is, on the reference design, there is a RF switch, for the TX and RX, but you can also implement a switch between the RF path and two antennas if you want. So this is possible. Of course, we can do that. Yeah.
Okay.
Thank you.
Question at the front.
I work with Bluetooth a lot and also with Nordic Semiconductor, and they provide this service that you send your design to them and then they check your RF design and they give you some tips, because mostly you make your own antenna as well, like PCB antenna. And I was wondering if Semtech also provides something like that or has plans to do something like that?
So, of course, if you have doubts in your design, if you want to check that that you follow the right guidelines, the right implementation for your RF, please feel free to send us your design and we'll have a look, of course. But we have also a lot of application notes. I didn't mention that, sorry for that, but we have application notes that give guidelines, how to implement RF design, how to tune, and so on. So you can check first those application notes, but of course, if you still have issues or questions, feel free to contact us.
Okay. Any more questions?
Small question. The slides, are these available? These slides?
Yeah, I think it should be, no problem, should be available, yeah.
Okay,
of course.
Thank you.
Okay. So if you have, maybe we are out of time, but if you have questions, I will be sitting at the Semtech table outside, so please feel free to come to me and we'll have, let's say, a longer chat. Okay.
Thank you, Olivier.
Thank you very much.